So this is my standard 0, which is the Lagrangian reassessment video number 1. I chose problem 31 from chapter 7 of Classical Mechanics by John R. Taylor. And the problem is a simple pendulum, mass m and length L, is suspended from a cart, mass m, that can oscillate at the end of a spring with force constant K, as shown in figure 7.15. Write the Lagrangian in terms of the two generalized coordinates x and phi, where x is the extension of the spring from its equilibrium length. Find the two Lagrange equations. So, to start off, this is a picture of the situation. The cart is oscillating back and forth on the spring, and it has a pendulum oscillating under it back and forth at an angle phi. So first, I have to find, there are two masses. One is mass little m, the other is mass big M. And I know that the velocity of any mass is just x dot. It's just another way to write it. So we need to find the Lagrange for both masses. So we're going to start with the little mass, and I know that the kinetic energy for a spring is 1/2 mx dot squared, and the potential energy for a spring is 1/2 kx squared. I also know that the mass for mass m, I need to find the r value. I need to get this distance in terms of r. So that is going to be the x displacement plus this is L sine theta. I'll solve the triangle right here. And for the x position, and then for the y position, it's just going to be minus L cosine theta. So then I have to take the derivative of that, and I get x dot plus L phi dot cosine phi in the x direction plus L phi dot sine phi in the y direction. So then I have to square that, and then after I square it, I end up getting a cosine squared plus sine squared that I can factor out, and then I get this. This is for the second mass. And then I know that the total kinetic energy of the system of the big mass is 1/2 m plus this x dot m squared. So these are supposed to be big M's right here. So then the potential energy is big M g delta y, and then the delta y is negative L cosine phi, which we saw for up there. So then the total m plus m we have to add for the translational kinetic energy becomes this. You just add them together, and the total potential energy, you just add the total potential energy for both of them. And then you plug those into Lagrangian for the total kinetic and the total potential, and you subtract them from each other. So then we get this equation. And we want to break it up into terms of x and x dot. So we solve the partial of L over respect to partial with x is equal to d over dt, the partial of L with respect to partial of x dot. And then this is the partial of L with respect to x. It comes out to negative kx. And this is turns out to be d over dt with the partial of L with respect to with x dot. And it becomes this. So then you set those equal to each other, and that is your first equation of motion. And then you do the same thing except for phi, and you get a few more terms, but they end up canceling whenever you set them equal to each other. So then this is your second equation of motion. And then those are your two equations of motion.